In the beginning, I wanted to thank Professor Ayman Mahrous for this invitation and EJUST. And this is the title of the lecture, Ionospheric Disturbance Investigation as associated with natural and anthropogenic hazard. This is the contents of presentation, but first of all, I wanted to give a brief intro about the lab I'm working in. Is PNT, or Positioning Navigation Timing Lab. And recently I will start to introduce my work, and I will explain 2 case studies about typhoon in Hong Kong and as a natural hazard, and the other one is Beirut explosion as man-made or anthropogenic hazard. This is a lab head, Professor Zhang Xiaohong, and he's also the director of the Chinese Antarctic Center of Surveying and Mapping. Also, Professor Leo is working in GNSS with INS and the orbital determination. And here is Professor Go Fei, and Associate Professor Ren. He's the head of our group for Ionosphere. And Zhou and Feng and me, I joined them. Also, we have more than 50 PhD and master students in related field. We have subgroups. The first group is working on precise point positioning, or PPP plus ionospheric investigation. The group head or group leader, Professor Ren, Xiaodu Ren, and also me, I joined them. And we have more than 15 PhD and master students. Here is a picture for a group meeting. Every week we have a meeting. And here is some moments for every semester. We have a meeting for the whole lab, like invitation outside for dinner. Here is a graduated student, PhD student. Last year, I was one of them. And here, master and PhD student from our lab. Here is some of current student and graduated student with the professors and teacher of our lab. The current project we are working in real-time monitoring for ionosphere, even for regional and global, and also the high precision for modeling the ionosphere with LEO satellite from GNSS and LEO satellite. Also, some project related to precise point positioning. Some of recent publication, we working in tomography from GNSS and simulation data from upcoming LEO constellation satellite, and also for tropospheric parameter like water vapor tomography. Here is a method or 2 methods here, comparison for global ionospheric mapping from GNSS and LEO satellites. And here is a study for, I want to indicate. Here is the study, we will speak in details about it later for the typhoon. And also mapping topside ionospheric vertical electron content from LEO satellite and from GNSS. Here is evaluation for international reference ionosphere and NICWIC from multiple LEO satellite. And this is an important also publication for evaluation for the global ionospheric maps provided by different IGS analysis center. It was in GPS solution in 2019. And the last one for publication here is a new method based on zero difference integer ambiguity to find ionospheric total electron content. Let's return back to the lecture. Let's start with introduction and background for our study or our lecture tonight. As it is known, Global Navigation Satellite System, or GNSS, refers to constellation and can providing us with data from positioning and navigation and timing from satellite to receivers. There are 4 constellations: GPS, GLONASS, and BIDO, and Galileo. This is a global, and also there is some regional like Japanese and Indian system. Also, there is a SPAS satellite-based augmentation system to improve the GNSS performance, and some of them is continental like EGNOS or WAS, and also some for country like Korea, and some countries made their system. Here is the ionosphere. As we can see here, the signal is sending from satellite is going through the ionosphere and could be disturbed. The ionosphere is extended from 80 to 1,000 kilometers above the Earth. And the crucial effect is from solar radiation is coming from sun and make charging the atoms. And then some free electrons is going, and the ionization happened. And after some time, the atom is returning to a neutral state, is recombination again. This almost recombination happened during night. We can see more details here. The ionosphere during daytime, we have multi-layers, but during the night time, some layers like F1 and F2 layer combined to one layer, F layer, and another layer like D region is disappeared during night. So the effect also of ionosphere is different than during night than the light, because the solar radiation is the crucial parameter. The regular variation or the variation in the ionosphere, we can categorize them two categories. First is regular variation, and this kind of variation is happened in diurnal or seasonal or annual or for 11 years. This kind can be modeled or pre-modeled in advance. But the other kind we focus on is irregular variation. And this one happened because of different parameters or different events, like space events or Earth-based event like earthquake or tsunami or volcanic eruption, and also man-made events like rocket launches and the nuclear explosion. As we can see here in this figure, the modeled value in black curve and the real value in red color, we can model it in the normal state. It's almost fitting with the real value. But during the storm, as we can see here, the real value is disturbed and the predicted value is not fitted with the real value. This is because of variation or disturbance, maybe is positive value and also sometimes is negative value. And for example, here for solar eclipse, it should be decreased because of solar radiation is already no solar radiation during the full solar eclipse, because of the shadow of the moon make the repletion in total electron content. The crucial parameter we should take in consideration in our study is the space weather indices, and we can conclude them in two parameters. The first one is solar activity, and they have frequently indices like F10.7 is solar radio flux, and sunspot number and solar flow speed. The other one is related to magnetic activity, and is the DST disturbance storm. This is the indices. The KB index also. This represents the magnetic activity. For the quiet or normal space weather, it will be like F10.7 is less than 90 solar flux unit, and the KB index is less than 4, is unitless, and also DST is larger than -20 nanotesla. In this case, we consider the space weather indices in quiet and don't contribute to the variation in the ionosphere. Otherwise, it may contribute to the variation on the ionosphere. The problem or general problem statement for this lecture and the research we will present tonight: electromagnetic or radio signals transmitted from satellite can be distorted by ionized plasma in the ionosphere, and this cause huge positioning errors, especially when we're using single frequency receivers, and also can lose track or cycle slip happened because of this ionized plasma, or we can call it discontinuity for the signal from the satellite to receiver. Precise determination of ionospheric variation is important in space weather analysis and also in navigation and communication application. The acoustic and gravity waves generated through natural and anthropogenic hazard become an important source of variability. This acoustic or gravity waves, this happened or generated during the hazard, like as I mentioned before, earthquake or volcanic or nuclear explosion. The methodology, here I will represent the general methodology for my strategy, and if there is some specific method, I will explain it later according to the case study. Here we're collecting GNSS data, especially from course station, because of it is dense course. We have good spatial resolution from dense course, and using carrier to code leveling. This method is has some advantage, like by leveling carrier to code, we can remove the ambiguity from carrier and also retain the precision, high precision from carrier, and minimize the noise in pseudo range code. Then we can get slant TEC value, and then we can use them directly or convert them to vertical TEC value. We will see the difference between them later. And then using the Detrending method, and I will show why we're using the Detrending method to find the ionospheric variation. And sometimes we propose some method, if the common method is not good enough or not convenient, we can propose some method to find the ionospheric variation. And for verify our result, we can check the space weather indices, and also using some EDIT data, like remotely sensed data or atmospheric parameter data, to analyze our finding. TEC value, or slant total electron content, the unit of it is 10 power 16 electron per meter square, and is the number of electron along the line of sight. This is the line of sight for the unit list, for the unit area. And this is the value of slant. We can calculate it, but the problem, we can't use it in mapping. because it is not projected value. Then we can convert it to vertical value by using any mapping function to find the projected value. Also, we can represent the ionosphere in shell layer or sometimes multiple layer according to the application. But we have to take care because the vertical TEC is not accurate enough in some application because of the projected value. It is projected value, not the original value. Why we using the Detrending method? We used it to remove the accumulated error in the ionosphere results, and also to find the ionospheric changes individually. These methods, I categorize them according to two methods. The first category is independent on days before event. There is some method here like polynomial fitting or Savitsky-Golay filter. We're using like sometimes fourth order, or fifth order, or sixth order polynomial to find or comparing the fitting value with the real value, and then can find the disturbance maybe happened or not. The other methods is dependent on days before event, especially if the days before the event in a normal state, we can consider them as a reference to find the disturbance during the event. Some method like interquartile range, and this is a common method, and the other method we proposed them in our research, like range of 10 days or enhanced average difference approach, and I will explain them later. The first case study I will show is Mangkhut typhoon. It was happening in 2018 in September, and it was in Pacific Ocean, Northwest Pacific Ocean. The problem statement for this work, although the highest amplitude of TEC variation have been recorded during the cyclone maximum wind speed. However, most of researchers have concentrated in the day of typhoon landfall. This is the last day of typhoon. Also, some researchers are using global ionospheric maps to detect the ionospheric disturbance during the typhoon. And as we know, GEMS have low spatial resolution. It is about 2.5 degree in latitude and 5 degree in longitude. And also GEMS, it depends on IGS station, and the IGS station is not well distributed, and also many places scarce for the IGS station, so it is not good enough for regional studies for the ionosphere, like our studies here. Also, atmospheric parameter, maybe also by depending on them, we can enhance the mechanism for the ionospheric or ionospheric coupling, atmosphere and the ionosphere coupling. The data we used is a course station from Hong Kong and also IGS station around the study. Also, the space weather indices, we will use them, and we can get them from this website. Here also is weather archive data about the typhoon. We can see the typhoon start from Northwest Pacific Ocean and going through Philippines and hit Philippines, and then going to Hong Kong and ended on 17th of September 2018 in southeast of China. Here is the air intensity or wind speed for the storm or the typhoon. As we can see, the maximum the maximum air speed or wind speed, it was about 250 kilometers per hour over 2 points. And at this point, we will analyze the ionospheric variation over 2 stations. Also, we use some atmospheric parameter, sea level pressure and zonal and meridional winds, and also some infrared satellite snapshot to monitoring the movement of the storm or the cyclone. To find the VTEC value over a specific point, like the point we need is maximum wind speed point, we suggest a method to find them. The old method, it was depending on the shire, and this is more convenient, especially for the gems, because it has big grid size, is, as I mentioned, 2.5 multiple 5 degrees. But we created our regional ionospheric maps, REMS, and it was the grid size is 0.2 by 0.4 degrees. So we can control in the starting and the ending point for our regional ionospheric maps, and then we can use the nearest neighbor to find the VTEC value for a specific point, like maximum spot or point of maximum wind speed. To detect the disturbance, as we can see here, we used different methods. First one is interquartile range. This method, we calculate upper and lower quartile and the median, and then find bounds, lower and upper bounds. We find the values for every hour. This is 0 hour. Every 2 hours, we can find the values, the lowest values and the highest values. And during these hours, this is the limits for to find the disturbance. We compare with the limits, the higher and the lowest limits. The last method, we used enhanced average difference by finding the average value for the days or 10 days before the event to find the most probable value, and compare with the day of the event the value for the TEC to find the disturbance. This is results for the typhoon. We can return. This is the methods we used to remember them. There is a method is interquartile range and range of 10 days and enhanced average difference. 3 methods to find the ionospheric disturbance or variation during the typhoon. So the result, as we can see, this is base weather indices over the whole period before and during and after the typhoon. It was almost in a steady state, except for 3 days and the day of 254. This day has the highest KB index is about 6, and we can also see the geomagnetic variation in the ST index. So this value or this day, we will exclude it when we calculating the average value and also interquartile range, because it may has some effect from geomagnetic. So if we calculating the average value, it will be make a scattering, and we can get the most probable value by including them. So we will exclude it when we calculating the average value to compare them. So the result for the VTEC value. As we can see here, the storm, it is continuous for 1 week. We studied the 7 days. And for the all days is almost convergent together, except 1 day is DOE 256. And this day, it was the second highest maximum speed, not the maximum speed day. Maximum speed day was 257, but the previous day was the second day of highest speed value. So this day has like higher VTEC, but now we can't consider it is a variation. We have to use some methods to know it is variation or not. The first method we used is interquartile range. Interquartile range, we make a condition. If the value exceeded the bounds, the bounds is lower, as we can see in pink color, and the higher bound. If the value exceed, like here we can see from 6, the hour 6, to the hour 14 in the horizontal, and this is the value for the TEC value in the vertical X. This is variation, and it is positive variation. Otherwise, the other thing is not variation, but only from 6 to 14. And almost the second station or the second maximum spot has the same behavior, because the two stations is close together, is about 100 kilometers between them. So for more confirmation, we used another method. It is range of 10 days. By calculating the lower limit and the higher limit with dashed line in pink and black color, and comparing with VTEC value for the DOE of 256 with blue color. And we can see it also has the same behavior and confirm with the previous results, with the previous method from interquartile range from 6 to 14. So this behavior, it already confirms there is variation in this time. Next, here we can see the third method we use is enhanced average difference. What is the condition to consider this is variation or not? We can see here only 2 days has variation. The first one is 254 and the other one is 256. But 254, it has moderate geomagnetic activity. So maybe the variation, it's related to the geomagnetic activity, not related to the typhoon. And the day of 256 has higher and significant ionospheric variation during the day and confirms the previous result. And also it is bigger than the value of standard deviation related to regional ionospheric maps or global ionospheric maps. It's bigger than the tolerance or the standard deviation of the modeling method. Then we try to analyze the atmospheric parameter, for example, meridional wind. As we can see, this is the anomaly maps. How to calculate this anomaly map? We calculated it from the average value from the previous 5 days. We can see here the previous 5 days, we can find the anomaly map. It is going to increase smoothly, but from the day 255 to to the day of 256, there is like critical change happened, or sudden change happened. So it is maybe we can consider the meridional wind. It's may contribute to the coupling. This is a suggestion, and to prove it, it need to do more research about this suggestion. The second atmospheric parameter we used is sea level pressure. And we can see here from the DOE from 255 to the highest variation or highest day of variation, we can see the value of a low pressure cell covers the largest area. If we comparing with the day of maximum wind speed, the white area is land area, and we focus on the sea level pressure, so it's smaller than the previous day. So the highest variation happened during the low pressure cell covers the largest area, and this confirms previous results. Here is infrared satellite snapshot to tracking the movement for the storm or typhoon with the point, is red triangle, is the point of maximum wind speed. As we can see here, this is different snapshot in different days, but the blue ones is number C and D and E. We can see here, this is the outer side for the typhoon. We call it is rim bands or edge, and this has severe or powerful more than the eye of a storm. The eye of a storm is more quiet. So the variation happened during, as we can see, 3 snapshots from 7 a.m. to 7 p.m., 7:30 p.m. We can see the point of maximum variation. It's close to the rim bands or the edges of typhoon. And during the next day is 257, is the day of maximum wind speed. It's close to the eye, the maximum wind speed point. It's close to the eye of the storm. So the maximum or the highest variation in ionosphere, it's happened during the day when the edge or rim band is near to the maximum wind speed point, and this also confirms previous results. The finding, it was a new finding here, is the maximum or highest variation observed during the second highest wind speed day, not the first highest wind speed day. This is what it was a new contribution in this work. And also the variation of space weather, we already consider them, and the space weather indices is not contributed to the variation for the typhoon. As we can see, it was in a steady state. Results also confirm previous results by Lee and Chen in 2020. The atmospheric perturbation in the eye of the storm or cyclone are fewer than those at the edges or rim bands or the outer side of cyclone. As a suggestion or new also suggestion, meridional wind and their resulting waves may contribute in one way or another to upper atmospheric coupling. That's all related to cyclone.